Hi guys, welcome back to my channel. Today we're looking at an application of first order differential equations. So let's just quickly do a little review of what a differential equation actually is. So we have some sort of derivative here, and it's only being derived once, and it's involved in an equation. And we would have to go ahead and solve for y in this particular instance. So to do that, let's just rearrange our equation. So we have dy dx is equal to 5y. Now I want to integrate with respect to my variable, but to do that I want to make sure that this dy is on the bottom here. So I'm going to actually flip my derivative here, so I have dx over dy, and because I've flipped this side I'm going to flip the other side as well. So now I can take the integral of both sides with respect to my variable y, and in this case these are going to cancel. I hate that term, but it's the best one I can think of to cancel these two dy terms. So now we have x is equal to 1 over 5 ln of y plus c. So we could now rearrange this and then we could solve in terms of y. So here I've rearranged to solve for y, and I'm pretty sure you guys would have seen a formula pretty similar to this in the past when looking at growth models. So why is growth an example of a first order differential equation? Well, with growth rate, say we had a population. The growth rate of that population, in other words, the change in the number of people over time, is proportional to the number of people that are already in that population. So when we have this is proportional to symbol, we can rewrite that using an equal sign. And so we will write equals to some sort of constant times by the population. So now let's go ahead and let's solve this first order differential. So just like we saw in the previous example, the first thing I'm going to do is I want to differentiate with respect to n. So I'm going to flip my derivative. So I have dt over dn is equal to 1 over kn. Now this 1 over k is a constant, so when I integrate this function with respect to n, then this is just going to pop out the front, and I'm going to end up with 1 over k ln n plus c, and that's going to be equal to t. So now what I need to do is I need to rearrange this function. So now that we've solved this differential equation and rearranged, we now have our general function for an exponential growth model. Let's do an example. The population of a city increases at a rate proportional to the current population. So in other words, dn over dt is equal to kn. In 2015, the population was 1.79 million, so we could write this as 2015 at time 0, the population was equal to 1.79 million. So I'll just write m. In 2019, so 4 years later, when t is equal to 4, the population was 2 million. What is the predicted population in 2030? So first things first, let's actually find an equation for this. And we know, because this is a differential, first order differential equation, that we can solve by integrating using that same process that we've done before. So we're first going to rearrange this. So dt over dn is equal to 1 over kn. Next, we're going to take the integral of both sides with respect to n. So that's going to get rid of those, and we're left with t is equal to this integral here. So this 1 over k is a constant, so that's going to come out the front, and then we'll end up with ln n plus c. Now this c here, it's always just some sort of constant. It doesn't matter if we're plussing or minusing this. It doesn't matter if we multiply or divide this value, because really we're not actually interested in finding the value for c. So I'm just going to pretty much ignore him when I do this rearranging. So we end up with kt, well, plus or minus c is equal to ln of n, and then we get excuse me, e to the kt plus or minus c is equal to n. So now what I'm going to do is, again, I'm going to let e to the power of c equal to some constant value, because, well, we know that anything raised to a constant power is also going to be a constant itself. So n will be equal to n naught e to the kt. So there we go. So there we have our general formula. Now we have some information here as well. The first piece of information that I know is that I know that the initial population is 1.79 million. So we have 1.79 is equal to n naught e to the power of 0. So in other words, 1. So then n naught must be equal to 1.79 million. Okay, so we've got our value for n naught. Now let's go ahead and let's find our value for k. So we can do that by using our other piece of information. So I've substituted my values into my second formula. So now we can go ahead, we can rearrange. So dividing both sides by 1.79 is going to give me e to the 4k. And then if I take the natural log of both sides, so 2 over 1.79, that's going to be equal to 4k. And so the last thing I need to go ahead and do is divide by 4. So our value for k is 0.0277. So we can go ahead and we can pop that back into our equation here. So now that we have this information, let's go ahead and let's determine the predicted population in 2030. Now, time zero was in 2015. So in 2030, our time will be equal to 15. So let's go ahead and let's substitute those values in. So n is going to be equal to 1.79 times by e to the power of 0.0277. And just notice this growth rate is positive, and that's why it's a growth model and not a decay model, multiplied by 15. So then all we need to do is just pop this into our calculator. And the solution that we get is n is equal to 2.71 million. Now let's go back to this original question. Does 2.71 million seem like a reasonable number of people? Okay, well, given that in 2015, the original number was 1.79 million, we had a small little jump 4 years later to about 2 million. And so in about another 15 years, yes, that seems pretty reasonable to me that that population would jump up to about 2.7 million. So that's an example of a growth model that uses differential equations. Let's go ahead and let's have a look at another application now of first order differential equations with respect to decay models. So a perfect example of something that decays is radioactive substances. So generally they'll have a half-life within 1,000 years, or some of them even with 100 years, or some of them have a really, really short time frame. So the more radioactive they are, generally the shorter their time frames. So what's actually happening is we are decreasing in mass in a given amount of time, and that's proportional to the original mass of the material that's remaining. So let's rewrite this using our symbols. So we can have the m over dt is equal to negative km. So I moved that negative to this side so that we can go ahead and solve. So I'm going to want to rearrange with respect to m. So I'm going to switch these. So I have dt over dm is equal to 1 over negative km. We can now take the integral of both sides with respect to m. So we can cancel those out, and we end up with t is equal to negative 1 over k ln m plus c. And again, this c doesn't really matter so much what the actual value of it is, because it kind of gets lost in the equation anyway. So now we can rearrange this so that we have negative kt plus c. And again, I've just put plus, it doesn't actually make a difference if it's positive or negative, is equal to ln m. And so the mass is going to be equal to e to the power of negative kt plus c. Let's go ahead and let e to the power of that constant equal to another constant, and we'll call that m naught. So now we have our function. So m is equal to m naught e to the negative kt. So the key difference between the growth model and the decay model, it's not anything to do with the derivatives. It's just literally that value of k is now negative rather than positive. So let's go ahead and do an example. The rate of decay of a radioactive substance is proportional to the amount of the substance present at that time. So again, this is going to be one of those problems where the change in mass will be proportional to the amount that's left. And we know, because this is decreasing, that this is going to be a negative value for k. So we can rearrange by swapping our derivatives, and we should also flip our other side as well if we're going to do that. And now we can take the integral of both sides with respect to m. So we're going to end up with T is equal to negative 1 over K ln of M and some other value. But again, we're not really interested in this. So when we rearrange this formula and we substitute in those values, we're going to end up with M is equal to M naught e to the negative kt. So that's our general formula. By the way, we don't necessarily need to do this differential equation all the time, but because this is such an important part of the curricula, I really do just want to drive that point home. So let's go ahead and let's read the rest of the question. Initially, 80 grams of a radioactive substance is present. So M naught is going to be equal to 80 milligrams. After 1 hour, it is observed that that 10% has disintegrated. So if we were to write at T is equal to 1, 10% has disintegrated. So that means that the mass at time 1 is going to be equal to 90% of what I had originally. So that's going to be 72 milligrams remaining. Determine the amount remaining after a further 2 hours, so when T is equal to 3. So let's go ahead, substitute the information we know into this equation. So we know that M is equal to 80 e to the negative kt. Let's use this information at time 1 to determine our value for k. So 72 is equal to 80 multiplied by e to the power of negative t because our value, negative k because our value for t is just 1. So going ahead, we can divide both sides by 80. So we have e is equal to 72 over 80 is equal to e to the power of negative k. And then we can go ahead and we can take the natural log of both sides. And I'm going to divide this through as well by that negative value for k. So let's pop that in our calculators now. So our value for k ends up being 0.105. Now hold on a minute. You said that this value for k should be negative. Keep in mind, I have gone ahead and I have divided it through by the negative value. So when we substitute it back into the equation is going to read M is equal to 80 e to the power of negative 0.105 t. So it is actually negative when we pop it back in the equation. All right, so determine the amount remaining after a further 2 hours. So in other words, when T is equal to 3. So M is going to be equal to 80 e to the power of negative 0.105 times by 3. So let's go ahead and let's pop that into our calculator. And then we have it. So the mass remaining is 58 milligrams. Does this seem reasonable? Does this make sense? We started off with 80 milligrams. We decreased that amount and within 3 hours, we've gone down to about 60 grams. Yeah, that seems pretty reasonable given the context and given that this material is decaying. So there you go. So those are some applications of first order differentials, so including growth and decay models. All right, guys, I will see you in the next video.